Hello and welcome, everyone. So we're going to be moving into the next lesson for our class. This is actually going to be two lessons, 2.5, depending on how you wish to view it and how much you want to go into this class. But it's going to be 2 to 2.5 lessons in one. So first, we're going to be talking about modeling and prototypes. So at various intervals of the engineering design process, conceptual, mathematical, and physical models are used to evaluate the design solution. So this is where a lot of your background work is going to go into play. Does get into the part where most people will consider the fun element of engineering, because you do get into things like prototyping, but there's still just a tremendous amount of work that gets done before you ever get to this point. Models are used throughout the engineering design process to make observations and develop predictions. Those observations and predictions are then evaluated, and if necessary, the solution is redesigned. So you're not just making models to demonstrate and test, but you're also using them to influence and guide your design as well. Models allow an engineer or designer to test ideas against real-world conditions without incurring the cost of developing a product. And so a lot of this is going to be is done virtually, or it's done on a scale, much smaller scale, or depending, sometimes actually a larger scale in the case of dealing with thing on like the microscopic level, where it's really expensive to do that. And so you look at how things would act actually in the macro scale. So models can be conceptual, mathematical, or physical. Keyword: mathematical. Okay, math just doesn't go away. Again, that's the math teacher in me, creeping out, but oh well. So conceptual models are abstract models that use language and graphic-based representations to convey meaning. They can include technical writing, graphs and charts, annotated sketches, and technical drawings. Now, we've already worked around a couple of these. We haven't done technical writing. Think things such as even instructions and directions in technical writing. Graphs and charts, you've already seen some of this in math classes. Annotated sketches, that's our orthographic representation that we worked on. And technical drawings, that's in our home styler that we're using right now. Technical writing is a very precise style of writing. Good technical writers practice clarity. They use accurate words, avoid jargon, abbreviation slings, and unknown terms. And brevity. Only use essential language that should be included. The key information should be stated first. When I speak, when I talk in class, I try to say what I need to say and use very specific terms in order to do so. And when I'm talking about the topic in general, I try and make sure and focus in on that point, and then only go to a side story. That is technical writing in speech. It is a process. It's not something that necessarily happens overnight. Good technical writers practice simplicity. They provide the necessary details, but do not use flowery language or needlessly complex language. Say if it can be said in 10 words, say it in 10 words. Don't say it in 20. Active voice. Use straightforward and strong language. Do not use passive voice. These technical writing is oftentimes in its own way kind of like instructions, and so this is what you tell people to do. This is what happens. This is what happens, not this is what we did. Don't use passive voice. Graphs and charts are commonly used to show a relationship between two or more variables and highlighting a trend or trends for the audience. You don't want to include too much within a single graph. There is an entire art behind graphs and their use and their effective use. When you cram too much into a graph, they become very difficult to read. So, keep it simple. Graphs and charts are commonly used to show data and results from evaluations. So you may not use a graph and chart in a mathematical model, in a conceptual mathematical model. Graphs and charts are good from things like surveys or actual experimental data and things like that, and because they help show what has already happened. Now, you can use graphs and charts in a pure theoretical sense, but if you're talking about theoretical, you're talking about things in the level of like, this is what we predict is going to happen, not this is what did happen. So you always have to keep stuff like that in mind when presenting good graphs. Graphs and charts commonly appear in the form of a line graph, which is used to show the relationship between two or more objects and or a trend. Make sure you pay attention to these because these are excellent quiz and test questions. So there's the line graphs. A bar graph used to measure the relationship by a relationship between objects by measuring the frequency. Or something like a pie chart, which compares parts and percentages to the whole set of data. So if we go back here just really quick, so line graphs show the relationship between two or more objects or a trend. So for example, height and weight, two things that are related, but we don't necessarily know how. There's the bar graph that shows the relationship by frequency, such as number of people that picked a red hat, a blue hat, or a green hat. And then there's something like the pie chart, which compares the parts of the whole. This percentage of people picked red hats. This percentage of people picked blue hats. This percentage of people picked green hats. You have something that like a Venn diagram that shows whenever you have multiple sets of data, and there is overlap between those sets of data. There are other graphs. There are other graphs that we can use, but those are kind of the more popular ones that you're going to see. We've already dealt with some annotated sketches. Again, that's our orthographic representation. Annotated sketches are sketches that includes notes or labels, dimensions, and/or symbols. In our orthographic representation that we did, we didn't include dimensions, but under most circumstances, you would probably keep you would probably want some kind of dimensions on there. Sketches are often used to show an idea or visibly capture a thought, and all sketches should include some type of annotation. Okay, there should be something in there just beyond the basic sketch. I noticed that in a lot of the orthographic representations that we did, there was a lot of information that could have been given with that wasn't, but it's okay because you know what, it was our first go round. Technical drawing is a visual communication language that is used to communicate how something works or is constructed. So there is specifics to how you draw something. It is a language. There are rules and there are things that must follow. All technical drawings include standard symbols and units of measurements. Again, in our sketch, we didn't put down units of measurements. And that's okay. That's okay. In that instance. But see, now as we're getting into this, we have to make sure that we include the units of measure when talking about finding the efficiency. I know I had a couple of people give me some answers, and I couldn't figure out where the number was from, because on one part of the page, I was writing numbers in feet. And then on another part of the page, I was writing numbers in inches. And when I did not, even though verbally I was stating feet and inches, in the actual image, I didn't have it. And so that left for some confusion. So you always want to include those units of measurements in there. Technical drawing can be produced using paper and pencil or on a computer using computer-aided design or CAD system. If you've heard me talk about CAD, that's why. There's this presentation 2.4.4. I'm going to post that in the classroom, and I'll let you take a look at it separately, because that's something that we won't be able to do with this class, and I'll talk more about that later. But it is something that you can do in your own time, and it does have to do with CAD. We'll use two basic types of technical drawing, which is the orthographic and the isometric. We've already talked about those two representations. The mathematical models, they are abstract models that use the language of mathematics. Again, word language here, mathematics is its own language. It is something that you do have to learn how to use the phrases correctly. But it uses the language of mathematics to describe behavior or solution. They can include statistical models, differential equations, and game theory models, computer simulations, and things like that. Mathematical models are used to to demonstrate traffic patterns in a city, or movements of birds as they're flying in the air, or movements of bees, and in biology sense, and for about anything that you could think of, there is a mathematical model out there somewhere that is trying to help understand that situation as to what's going on. This stuff is used. The unfortunate element is that most of it, you don't see it get used within the high school setting. So that's why it seems so alien to most of us. Mathematical models are used to simulate how a system or product might behave. They frequently use symbolic algebra to represent and explain mathematical relationships. So there's your variables. Computers are often used to improve mathematical models by performing long, complicated, and or repetitive calculations, iterative calculations especially. Differential equations are equations that, especially in ODE, partial differential equations, there are calculations, simulations that in order to get accurate information, I ran, anywhere from 10,000 to 1,000,000 calculations that the computer was able to spit out in a matter of seconds, which would have taken me, potentially even a lifetime to have done those calculations by hand. So, the computers are a great advantage there. Mathematical models are used to express ideas precisely. So we can do stuff in math that allows us to operate in the realm of theory that we can't do realistically. And so from that, we can actually ascertain a precision in math greater than we ever could in the real world. Prior to developing the mathematical model, you must first determine the output of what you would like the model to achieve. Output or what you would like the model to achieve. The available data or what information can be used in the model, and the research, what research has been done to develop similar models. This is a beast all unto its own, and there are classes dedicated to just working with these bullet points, and so I'll just kind of let those rest there and not go too much into trying to explain them. Okay, once the background information and output have been developed, you should identify relationships among variables, create and use equations that relates to those variables, and then check the model for accuracy against similar systems or products. One of the ones that I really enjoyed doing was we did a wind tunnel test, and we got to use some Navier-Stokes equations and simulate what we thought would happen when air went over this particular model, and and look at the computer and what the computer said should happen, and then look at what happened actually in real life, and and things were actually pretty accurate. We did notice some differences, which were accounted for some loss, some energy loss, and some things that we hadn't thought of. But it is really neat to see that kind of stuff, come together. And the high school math is really just the foundations and on how to do that kind of stuff. The physical models are the 3D models that represent the solution. So this is what a lot of people think of whenever they think of engineering, or more specifically prototypes. They can include mock-up, a representation of the final solution that does not function. So if you've ever seen what a new design on a car looks like, but yet the car never moves. That would be a mock-up. It might just be the exterior of the car with no engine. And then the prototype performs the final solution and can be used for testing or evaluation. So the prototype is the working model, whereas the mock-up is one that just doesn't do it at all. A mock-up is a scale or full-size model primarily used for testing and demonstration. Mock-ups are primarily used by engineers, designers to collect feedback from potential users. Whereas a prototype is full-scale or full-size working or partially working model. It doesn't have to be completely working. And prototypes are used by engineers, designers to test and evaluate the design to further develop the product. And so when you create your prototype, you're almost guaranteed not to be done yet. That's something that you do have to kind of keep in mind. You're not actually done. You're just testing it out to see where you need to go from there. All right. This next one, I will post this in the classroom because there are some links about the 3D modeling software. And but I do want to point out, before you get into three-dimensional modeling, you really need to think through what you're going to be doing. You can't just start building and hope that you get there. You have to already have a pretty solid understanding on what you're making and how it's going to work before you ever actually get into trying and designing it. And then and then these others go into the idea of universal design and testing. So I'm not, first off, you can pause. You can pause, and I am posting this in the classroom, so I'm just going to move through these really quickly. They talk about the Autodesk Inventor software. It's you can get like a free trial with Autodesk, and but this is one of those, it requires a download, and so it's not something that I'm going to be able to take you through as a class as a requirement. It is something that you can do on your own. And when I post this in the classroom, you should be able to access these web links in just the same way that I do. So I do want to point out that there's two different ways, two different primary ways that you can work in modeling, which is additive modeling, which is assembling the pieces together, and then there's subtractive modeling, which this is like what the sculptor would do, where you take away pieces in order to generate the shape that you want. Okay, so there's some pretty good links here to be able to use Inventor. So if this is something that you are interested in, more than happy to provide the material for you, but unfortunately it is something that as of right now I can't really take you through. So we're going to be working primarily with HomeStyler and those programs. All right, the last one. We've already done some of this, so I'm gonna move through it very quickly, but calculating area and volume, we've seen it just a tiny bit in working with the efficiency and a couple of other problems. But long story short here is you need to be able to calculate area, surface area, and volume whenever you're dealing with engineering. One of the thoughts that I currently am kind of mulling over in my brain is, in the house design project, do we want to try and calculate how much printer ink in the 3D printer, it's actually not ink, it's plastic, but how much printing material do we expect our designs to use? And I mean, that's totally a volume problem right there. So I've tossed these terms around a lot, but now we're just bringing out and further defining them. Area is the amount of space inside a two-dimensional shape. The surface area is the total amount of area on all surfaces of a 3D object. And the volume is the amount of space in a 3D object. So area, we're talking 2 dimensions. And volume, you're talking 3 dimensions. The surface area is area, which is 2D, on a 3D object. So finding the equation for area on a square, that is just the side length squared, or side times side. What makes a square? All the sides are equal length. 90 degrees rectangle is all corners 90 degrees, 4 corners, and then it's just the length times width, or in this case they view it as width times height, which it's really the same thing. It's just a matter of semantics as to how you name it. A triangle, so a three-sided figure. If you know the base length and you know the height. Now notice what they are stating as the height. Okay, it is from the distance from the top tip down to the base. It is not this side length. It is not the side length. That is something different. And so the equation for the area of a triangle is 1/2 base times height. You could also view it as base times height divided by 2. Area of a circle is pi, which is approximately 3.14159. It's pi times the square of the radius, or pi r squared. Calculate the area for the square on the rectangle. If the side length of the square is 4, it's going to be 4 times 4, which is 16. This rectangle is going to be 3 times 2, which is 6. Okay. So notice with these, we're not putting dimensions on them, and that is because it would be true no matter what the dimensions are. So if I have a triangle that has a base 4 and a height 3, my result, which is going to be 6, would be 6 whether I'm talking about if it was 4 inches by 3 inches, if it was 4 miles by 3 miles, and so on. And then the radius, that's going to be 2.25 squared times 3.14. I don't have a calculator on me, and I can't do that one in my head. There. So the square of the radius, 2.5 squared, is 6.25, and then times pi is 19.6, approximately. In surface area, it helps if you can to create what's called a net, which is, imagine if you could take that 3D shape and unfold it. In the case of a cube, if you're trying to calculate the surface area, if you look at it, it has 6 square faces. And a cube, all sides are equal, so if you just find the surface area, if you find the area of one face, then you can just multiply it by 6 and find the area of all faces. In a rectangular prism, you got to be careful with in looking at these equations, because there's actually some other ways to calculate the surface area, and that you can learn in math 3. If you take a look at this, what is actually the side, so what's this face that's here in the front, depending on how you're perceiving it. I have this face in the back, and then the face that's here on the left, or sorry, that's on the right, and that's on the left. If you look, they form the perimeter of this top prism, and both of those are just times this height w. So you could also do the perimeter times the height plus twice the surface area of the top and the bottom. But that's a different equation altogether. And if you can follow through that, in audio, that's great. If you want me to talk about it in class at some point, then I can certainly do that as well. But ultimately, if you look, you have 2 faces that are, the left and right, which have dimensions d and h, so that's right here. You have two faces, front and back, which is w and h, right here, and 2 faces, top and bottom, which are these 2 right here. Add those together. Surface area of a sphere, unless you want to get into some calculus, then you just have to trust this particular equation. When you know the radius, it's going to be 4 times pi r squared. For a cylinder, you get into that perimeter thing that's actually going on, because if you take this lateral face, it's got a height h, which is right here, and then the perimeter of a circle, which is the circumference, is 2 pi r. So that does work here. And then you have 2 circular faces. So area of a circular face is pi r squared, and you've got 2 of them, so multiply it by 2. All right. Can I do this in my head? Can I do this in my head? There's 6 faces with 2 squared, so that's going to be 24. That's going to be 24 square units here. Pause the video if you want to try and beat me to this one, but this is going to be, let's see here, 8, 12, 36, and 36 plus, let's see here, this is going to be 8, 16, 16, that's 46, 54 square units, I believe. Oh, I was off just a little bit here, 52. So, oh well, I missed it. Calculate the surface area of the sphere and the cylinder. Pause them now if you want to try these on your own. I'm going to go ahead. I'm not going to try and do these in my head, because I could give it to you. I could give you the answers in terms of pi, but you know, as for calculating 3.14 in my head, I couldn't quite do that. So here's the answers. Here's the answers for these. And feel free, if you know, at the time that you were watching this video, if you're watching this video in class and not later, then you know, I may not be able to answer these questions right now today. But if you have questions about them, we can always come back to them at another day. And then volume. So a cube, and the thing about it, there's a branch of math in calculus that we get. If you go on and take calculus, you know, you may fall into this trap of thinking that everything in calculus is integrals and derivatives. If you don't plan on taking calculus, you don't know, you know, you're not going to hear anything about those and just think that's some weird math thing. But they're incredibly important. But there's another element of calculus, which is just breaking things down into incredibly small pieces. Incredibly small pieces. And the smaller that you break those pieces into, the more accurate that your total result is going to be when you add everything together. And when it comes to volume in incredibly complex shapes, you know, just like how computers have pixels, computer images have pixels, you can mathematically cut objects into these incredibly small, you know, objects like cubes, which are something that we can compute. The volume of a cube is just, you find the length of one side and then you multiply it by itself and multiply it by itself again, or you cube the value. Rectangular prism is the width times the height times the depth, d, in case you were wondering what d was. But you know, you may also say length times width times height. And it just, you know, that's just kind of depends on you know, what you're going for. The volume of a sphere, 4/3 pi r cubed, and the volume of a cylinder is pi r squared, which is the area of a circle, times its height. So there's actually if you go in, when you go into Math 3 and you learn to find volume by base area, you'll actually see that you calculate the volume of a cylinder and the volume of what's called a prism the same way. So calculate the volume of the cube and rectangular prism. So if the height here is 2, it's going to be 2 times 2 times 2, which is going to be 8. And for this rectangular prism, this is 4 times 2, which is 8, times 3, which is 24. And once again, so this is 4/3 pi r cubed for the sphere, and that's going to be 4/3 times 2 cubed, which is 8, and times 4/3, that's going to be 32 over 3, which is about 11, which is about 11. And then you're going to multiply it by pi, which is about 3. So you're going to get about 33. It should be more than that. And look there. There's so that's kind of how I do pi. I didn't look over at this one, but point 0.15 times 6. Or sorry, 1.5. Yeah, I'm sorry. That's can't quite do that one in my head. 2.25. That's what I couldn't get. And then times 6. Yeah, that's going to be 12, 4. 12, 14, and then times about 3. So yeah, that's coming up about right without a calculator. So you're going to want to be able to do these calculations and do these calculations rather rather smoothly. If you have any questions on them, feel free to ask me, and and then we'll wrap up and go from there. I hope that this. I hope that this wasn't too much information. I apologize that I can't be here, for this lesson. This is predominantly to my third and my fourth. And but anyway, if you have any questions, shoot me an email. Otherwise, we'll see you in class, and have a good day.